Hello, Physics 2211. Today we're going to be using the momentum principle and the energy theorem to describe the physics of a board break. If you're unfamiliar, a board break is a common way for martial arts schools to demonstrate their talent and obtain new members, but we'll be breaking down what it actually takes. Today, we'll use Tracker to analyze a video of a board break and then use the energy and momentum principles to create an iterative Glowscript model to calculate the energy required to break the board. After, we'll look at an estimated energy value to break the wood and compare our answers. First, you'll need to understand the energy principle, momentum, and pressure. The energy principle means that the total energy in a system is equal to the total final energy of the system unless there is work done. Work is equal to the change in energy. In our system, we have our hand and our board. All of the initial energy is concentrated in the kinetic energy of my hand, and then afterwards, the kinetic energy from my hand is transferred to the board in the form of internal or thermal energy and kinetic energy. The change in internal energy of the board is what causes it to break. The momentum principle is necessary so that we can use the maximum force applied by the board to figure out the change in kinetic energy of my hand as a part of the energy analysis. While the board is absorbing energy from my hand, it slows it down, and we use the momentum principle and the force supplied by the board to determine how much my hand slows down based on the maximum force the board can supply. This is why we need to know what pressure is, or force over area. We use the pressure rating of the wood to determine the maximum force that the board can supply, decelerating my hand. In the tracker model, we supplied the masses of both parts of the board, assuming they are evenly split, as well as an estimate of my hand and forearm. We use the distance over frame to calculate the velocity of my hand directly before making contact and directly after making contact with the board, as well as the velocity of the board, or one end of the board, as the other end is being held constant. We find the linear velocity of the board and will later use it and the length to find the angular velocity. In the Glowscript model, we use the initial conditions from the tracker video, but ignore my hand's acceleration and use only the velocity immediately before striking the board. We also make our calculations in several different loops. One to move the sphere representing my hand, another to slow down the sphere representing my hand and accelerate the wood, and another to rotate the two equal pieces of wood at a constant angular velocity after contact. Using this simulation, we find the final velocity of the fist, and we use that for our energy analysis. We calculated that my fist and the board lost 3 joules of kinetic energy, meaning 3 joules of kinetic energy were absorbed as internal energy and were used to break the wood. We did this by using an energy analysis. We calculated the total kinetic energy of my fist initially, and subtract the final kinetic energy of my fist as well as the final kinetic energy of the boards, assuming all other energy is absorbed by the board in the break. The actual estimated energy used to break 1-inch thick white pine wood is about 5 joules. So why was there a 2 joule difference? So some assumptions that we made is that the hand is a surface that is 6 inches squared, and the only forms of energy involved are kinetic and thermal. We also assume that the board absorbs all of the thermal energy. However, there are people holding the board that probably absorbed some of it as the board rotated. So how do things break anyway? The kinetic energy absorbed by the board is what causes it to break. So essentially, we just have to move our hand fast enough. This is why almost anyone, when given proper instructions, can break a board. We're told to punch through the board so that our fist has enough speed and the board cannot provide enough force fast enough to reduce the fist's speed to 0. As you can see, it required at least 5 joules of kinetic energy to break the board. Another way to think about this is using impulse, or force times time. This is also equal to the change in momentum. So a large change in momentum over a smaller amount of time can cause more concentrated damage and break an object as opposed to pushing it or bending it. Hope you enjoyed!